And I'm following in good footsteps. All right, so let's go back to that example of BSBT, which I deleted, but so, I mean, we determined what L squared of C bot was, right? And that tells us that if we pair these two things off against each other in this Lefschetz form, then this is this guy paired with L squared of himself. And we computed the coefficient of C top inside this guy, right? Which was exactly lambda times 2 delta minus ATS lambda. By the way, remember that ATS is negative. So minus ATS is actually positive. Okay. Okay. So if this is positive, then we have Hadriman, and if it's negative, then we don't. Okay. So we're asking, is this bigger than or equal to 0? If it's 0, of course, then the form's degenerate, and it doesn't have HL at all. So you have this sort of same diagram, right? Here's lambda equals 0, and let's say this side is lambda bigger than 0. Here's 2 delta equals lambda ATS, and then maybe like one of these sides is positive. And so you have HR inside this region where they're both positive, and inside this region where they're both negative. And then you have sort of HR with the opposite sign, so it's negative degenerate here. Oh, give me a sec. Sorry, I just realized I forgot to say something up here. Yes. So this is supposed to be alternating definite on primitives. And all I did was check that it was positive definite on the lowest. Oops. But actually, so what I can do is look in degree 0, find the kernel of F, L explicitly, pair it against itself and see whether it's positive and hope it's negative. And in fact, the condition that you get, and this is a good exercise, is exactly the same condition. Why? Yeah. So this is enough to check. But why, actually? Already you know this because Hadriman is determined by the signature. Okay? Now the signature at degree 0 doesn't depend on L at all. Degree 0, the Lefschetz form is the same as the regular form. It has signature 0. That's just something you check. Okay? So in fact, the signature in degree 0 doesn't depend at all, and all you need to check is the signature in degree -2. That's another reason why this was enough of a check.
So could you just go over it again?
Right. So you have this and this and this. Maybe I didn't draw it in that order. Okay. And it looks like this. And so this guy is the primitive in degree -2, and some linear combination is the primitive in degree 0, because whatever it's in the kernel of L. Okay? And if I claim that if it's positive definite here, that must be my negative definite here, and vice versa. And the reason is because if it's positive definite here, then it's positive definite on the image. But the signature is 0, which is just a fact, which doesn't depend on L at all. So if it's... Exactly. So the other one must be negative. Okay? So that's the argument I was making. But you can also explicitly check, and you compute the signature on this guy, and you'll actually get minus this, and that's supposed to be negative. Okay, so this is a worthwhile calculation to make sure you believe me. But the idea that again is Hadriman is an open condition. And in fact, if you look at the things that have hard Lefschetz, it breaks it into chambers, some of which have Hadriman and some of which don't. So I'm going to make that into a claim. Given a continuous family let's say L zeta of operators with HL, if any of them has HR, then so do they all. Okay, so here's a family of polynomials, say, they all have HR. I can't do something like this because that crosses over a point where it doesn't have HL. So this condition that they all have HL is super important. Okay? And the proof is sort of, that you have this in each degree. You have this family of Lefschetz forms. This is a family of non-degenerate forms. So the non-degenerate is from the HL property. Okay? And signature is constant. So the signature can't change on a family of non-degenerate things because the signature is valued in a discrete set. Signature can change in a family of things that aren't all non-degenerate. This will lead to a nice argument. So this is kind of called a limiting argument. All right, it helps to do certain arguments. So for instance, if lambda and delta are both positive. Okay, so remember that minus alpha st is a positive number. Now, all the coefficients here are positive, so this number must be positive. Right? But maybe there were some negative coefficients, but we knew, but then we knew that the positive coefficients were much bigger than the negative ones. So we could take some very, very high value. If we know that when lambda is very, very, very large, and we have a Hadrimon, and we have some continuous family of things that have HL, then we can deduce that they all have HR. So that's the kind of way in which this claim is useful. And there will be already examples like this. Okay. So let's state the main goal. So given an R bimodule B, B bar is this thing that I've been writing as B mod R plus, or maybe B tensor over R. So I'll just put notation. Okay, kill action of write things on the right. This thing we usually call the right quotient. And so again, I haven't really been, I've mentioned several times that there's some duality functor. I haven't ever described it, but it's not so hard to show that if B is self-dual, then the dimension of Bi, of B bar I, is the dimension of B bar minus I. And also, since I said maps from this to that are correspond to invariant forms, and isomorphisms correspond to non-degenerate invariant forms, B is also equipped as a non-degenerate invariant form. B bar. Actually, B has a non-degenerate R-valued form, which becomes non-degenerate when we pass through the quotient inversion.
What is B?
B is an R bimodule, say free as a right module. So for instance, any Zergel bimodule. This is on the exercises. Okay? And as it's an R bimodule, left action of a polynomial does something. So left action of any linear polynomial is a Lefschetz operator. Okay? And so our goal is this. So choose some row in H dual, i.e. a linear polynomial. Okay? Such that ds of rho is positive for all s. Okay, so for instance, this is where lambda and delta are both positive. Okay? Then take the indecomposable Zergel bimodule BW and its right quotient, and this corresponding Lefschetz operator. And what form? Okay, so actually, you know, it has a non-degenerate form, but I'm going to take one which is not a priori non-degenerate. I'm going to take this induced form, and I'll say what this is in a sec. This thing has HR. Well, because we define the global intersection form on Bot-Samuelson's. And this is some random summand. So actually what I mean by this is the restriction of the global intersection form on a Bot-Samuelson associated to any reduced expression restricted to the summand. Yes, and so this actually depends on the reduced expression. They could absolutely be different. Okay? So for any reduced expression. So maybe I should say for all W underlined restricted to BW the summand. Okay? So this is not a priori non-degenerate. Okay, but part of this whole proof, inductive proof, will show that it is. And in fact, you know, this is all well and good. So, I mean, why don't we just show that the Bot-Samuelson, that it has HR on the Bot-Samuelson? Why do you think we're not doing that? So why do you think that we didn't just say, oh, well, the global intersection form on the Bot-Samuelson has HR? Why is that not our goal? Because it's not true, yes. But why is it not true? And you've already seen an explanation. The explanation was when we did BS. Now that's not a reduced expression, but so BS couldn't even have HL because it had a shift. Okay? So, I mean, if this goal is true, then if you take BW and shift it down and add it to BW shifted up, this cannot have HL. This is also going to be on the exercise sheet. Okay? And so a Bot-Samuelson...
Just because the signs are not correct?
No, yeah, because because the summands cannot, because the Lefschetz operator preserves the summands. And so if you take a summand and shift it, then it's no longer balanced around 0. And so something that's not balanced around 0, it can't possibly have HL. So, so a Bot-Samuelson, some of the Bot-Samuelsons, like BSBT, when you decompose them into indecomposables, have no shifts. But some of them have shifts, and so they can't possibly have. So in fact, if they have no shifts, then they'll have HLR as well.
The fact that there is something compensating which is opposite shift doesn't really matter because each individual thing
Yes.
by itself needs to have a problem.
Exactly. So the statement, you know, is that, you know, why not BS? And the answer is because BSW is not semi-small, which just means that when we write it as an isomer, as a direct sum of various indecomposables with shifts, okay, that not all shifts. So semi-small is the statement that when we write it as indecomposables with shifts, that n is always 0 for each sum end. Okay, and Bott-Samuelsons are not semi-small in general. They can be, but in general they're not. Okay? So that is the problem. Whereas something semi-small will in fact have the Hartree-Mann bilinear relations.
So when you, are these orthogonal or different indecomposables?
Right. Because there's all these sorts of different indecomposables. Are they orthogonal? Yes, they must be. Because they're preserved by the Lefschetz operator. No, they're not orthogonal. They're not orthogonal. Absolutely not. In fact, BS is a good example. The two copies of BS are basically paired off against each other. So even though hard Lefschetz is false. Yeah. And in fact, when you shift it up, the form can restrict it to be non-zero. But when you shift it down, the form restricts it to it be 0. So this is an interesting feature as well. So there's going to be an example of this in BSBS. This is going to be on the exercise sheet. So don't worry about that too much. It'll become clear in the exercise. In fact, one thing that is semi-small, and this was something that we recall from the original construction in the Heck algebra for the Castellan-Lustig basis. Recall that BS times BW, when S increases, is semi-small. Okay, or at least it's semi-small if Zergel's conjecture is true. Because on the Grothendieck group, HSHW was HSW plus a bunch of lower terms with these integer coefficients. These were true integers and not polynomials. This was part of this whole computation. And so in fact, what we're going to show is that BSBW has HR. So the better goal and a harder goal, well, no, it's not harder, sorry, is that BSBW L rho, and then again, the induced form. So this shows up inside the reduced expression of W with an S before it. Has HR. And this is going to give you a rough idea. Sorry, I'll let you write it down so that you can both write and follow. This is going to lead to our inductive proof. Okay, we're going to show that BW has HR. We're going to somehow bootstrap into the statement that this has HR. And then we're going to say, okay, well, the summand inside it has HR. And we're going to repeat. Okay, so thanks to semi-smallness, we can do this nice argument and always talk about HR. There is something you can do when you're not semi-small. Okay, it's called the relative Hartree-Mann bilinear relations. It involves having two different commuting Lefschetz operators. And this is just much more complicated. Okay, so I can describe it to you some other time. So the point is that and we still haven't actually successfully proven that Bott-Samuelsons have the relative Hartree-Mann bilinear relations. They do, I assure you of this. But we're having a little bit of a couple technical difficulties in the proof. But
You mean that would give you a different.
that would give you a different proof
Without having. Maybe.
without having to do sort of a more annoying induction. I mean, you still have to do an inductive argument there, but without sort of relying on the semi-smallness to cheat a lot. And it would help you, yeah, it's just a much nicer fact. It also proves a couple other positivity facts. So, it's a good thing to show. It is a very natural thing to show. In other words, the decomposition theorem for semi-small maps is not, people don't prove that. People prove the decomposition theorem in general. You should have the general version. But
you need to find the right statement. That's what
exactly. And so the relative Hodge-Riemann bilinear relations is the right statement, and it's just more complicated. So the fact that the main goal, so including this, implies the Zergel conjecture will be next time. But the basic idea is to show that the local intersection form, which is the thing that governs what splits off. Remember, we take two light leaves and we pair them off against each other and we find the coefficient of the identity. That this embeds into a Lefschetz form, into the Lefschetz form. And in fact, it embeds into primitives inside a certain degree. Okay? So that if this has HR, not just HL, but HR, right, so we are interested in showing this is non-degenerate, right? We don't care if it's definite, positive definite, but we care about showing it's non-degenerate. Well, it embeds into a space which is positive definite or possibly negative definite, depending on the degree. So if you restrict a definite thing to a subspace, it's still definite and therefore non-degenerate. Right? In general, if you just embed something into non-degenerate, a subspace could be degenerate. So this definiteness is really important. HL, hard Lefschetz, is really kind of the crucial property, but in order to prove it inductively and et cetera, you need HR. So this idea dates back to Di Cataldo and Migliorini. They basically gave an alternate proof of the decomposition theorem, and in this whole thing, they're bootstrapping and using induction, and it was really crucial that you use HR to prove HL. You have to think of them as separate. Even though HR implies HL, these sort of statements are crucial. So embed an arbitrary form inside something which is positive definite, then it can be non-degenerate. And this is where we use the real numbers.
So until this point, it's okay.
Yeah, exactly. Until we started doing HR, until the discussion of HR, yeah.
But Hodge-Riemann is stronger than.
Hodge-Riemann is stronger,
So
but you should treat them as separate when you're doing induction. And the reason is because of this claim, which is that if you have a family of things with HL, and one of them is HR, then the rest of them have HR. So first you sort of inductively prove that things have HL. When you're doing HL, you can ignore degree 0 because it's trivial. Then you show that one thing in this family has HR, and that involves a real interest in degree 0. You have to compute the signature there. And then you use this limiting argument to say that, in fact, they all have HR.
And then keep going.
And then you keep going. It's a really clever thing. It's really very clever. So, I'll talk about that, I guess I'm mostly out of time. I wanted to. Do you mind if I go for another 5 minutes?
No, not at all. But
So.
One more thing, the local intersection form and the global intersection form, how are they related?
I remember, so the local intersection form was for some particular, it was for any Zergel bimodule. It was going to tell you what things are summands of it.
But that sort of depends on in where you realize it.
Yes. So for instance, to prove the Zergel conjecture, we could prove that we categorify this formula. Now give us an inductive proof. If HW is the right size, HSW, we know how big that is. all these lower terms have the right size. So if we could show that we categorify this formula, then by subtraction, this thing has the right size. Okay? So basically what we want to show is that inside BSBW, each by shows up with this multiplicity. Right? Well, this is this dimension of the Hom space. So if we show that each Hom is an inclusion, then it shows up with the right multiplicity. That was the local intersection form. So the local intersection form said how many of these Homs are inclusions. And if it was non-degenerate, then all of them are, and it has the right multiplicity. So the local intersection form was on Hom from By to BSBW. Okay? Now if you evaluate this on C bot of By, whatever that is, then you get an element inside this thing. You get an element inside the right quotient. That element is primitive in degree minus the length of y. That's what you have to show. And if you show that, then Hodge-Riemann on this implies, and that this is an isometry. That evaluation on C bot is an isometry for these forms, or at least an isometry up to a positive scalar. So if you show that, then the Hodge-Riemann bilineations imply that this form is actually definite. So that's going to be but I was going to do that next time.
Oh,
Okay. But the key step is this induction. And so I said that somehow we bootstrap BW, some statement about BW, into a statement about BSBW. And what's the relation between the two? Really sort of they're graded, they have different graded dimensions, they're different spaces. What we have though is a map between them, which is the dot on BS. And so we have to somehow turn that into, and use that structure in some way. So suppose so suppose that sigma is a map from a graded vector space V to a graded vector space W. Okay, these things both have their forms, and they both have Lefschetz operators. Okay? Now, sigma has degree +1. Okay, so it sends Vi to Wi plus 1. And suppose that with respect to the Lefschetz forms, so suppose two things. Suppose that sigma commutes with L. Okay? And suppose that with respect to the Lefschetz forms, V prime, in degree minus I LV, sorry, this is sigma V is now in W, in degree minus I plus 1, that this is the same thing as V prime in minus I for LV. So it's an isometry for the Lefschetz forms. Okay, well, this is a weird thing. Why would something be an isometry for the Lefschetz form? Well, you'll see why in an example soon. You'll see why. Okay? So suppose this. And then finally, suppose that sigma is injective from negative degrees. So from Vi when I is negative. Strictly negative.
It's an isometric operator.
Say that again?
It's an isometric, right?
Yeah, but I never said, I never assumed HL. So this Lefschetz form could be 0. Right. So I'm trying to bootstrap something about W to something about V. Okay? And finally, suppose W has HR. So this is really important. We need HR and not HL for this argument. Okay? So given these suppositions, we're just going to explore what can we say about V. So choose a vector which is primitive in degree minus I. Okay? Now, it's non-zero. Okay? Then sigma V is also non-zero. Hooray for injectivity. So assuming I is positive. Okay, so we're really working in negative degree here. So sigma v is non-zero. Okay? But it doesn't have to be primitive. Okay? So it maybe has a primitive part, and then it's L applied to a primitive part, and then L squared applied to a primitive part, etc., where all these Wi's are primitive in various degrees. This is the Lefschetz decomposition. Okay? Now, what we're going to try to show is HL for V. So we want to show that L to the I of V is non-zero. Okay? Well, L to the I of sigma V is L to the I of W0 plus L to the I plus 1 of W1 plus dot, 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 dot. Okay? Now, W, okay, so this is just applying the formula. W0 is in degree minus I plus 1, and he's primitive. So L to the I of him is 0.
W0 is in degree minus I plus 1.
Exactly. And he's primitive, which exactly means that this is 0. But this, for instance, is an injective map. So if W1 is not 0, then this is not 0. And in fact, each of these terms, each individual one of these terms is non-zero if Wi is non-zero, because of hard Lefschetz on W. So all we've used so far is HL on W. Okay? So if W1 is non-zero, or W2 is non-zero, or W3 is non-zero, then this is non-zero, which means that Li of V is non-zero. Okay? So if some Wi is non-zero for I bigger than 0, then Li of V is non-zero, which is what we wanted to show. So now we have to show it in the other circumstance. I'll finish the proof right here. Okay? So now suppose that, that sigma V is just W0, i.e. it's primitive. So suppose that sigma actually sends this primitive thing to a primitive.
So each of them are individually non-zero.
Yes. So why is there some non-zero? Because they're in different isotypic components. Exactly. Because it's really a decomposition. So now suppose that sigma actually preserves this primitive, sends a primitive to a primitive. I mean, the picture you should have here is this. Here's V. Here's W, it's a little shorter. Here's sigma, going up like this. Okay, so here's V, here's W0. Okay? So now we want some sort of argument that Li of V is non-zero. Okay? But, you know, Li of W is clearly off the charts. Okay? But now we have this beautiful fact, and here we use the isometry. Okay? So V paired with himself, okay? We're trying to show that this is non-zero. Right? Or certainly, if this is non-zero, that certainly implies Li of V is non-zero. Okay? But this is equal to sigma of V paired with sigma of V. But this is primitive, which means that this is positive or negative. Okay, so this is certainly not 0. Here we used HR. Okay, this is positive or negative, depending on some sign. Okay, so now that implies that Li of V is non-zero. Two really nice separate arguments. Okay, do you preserve primitives? If so, you use Hajriman. In fact, is there any non-primitive part of you? If so, then already it's easy. Okay, so this is the easy case and this is the hard case. Okay? And so the result that we get is HL for V. Now I can state this in a proposition. So this is our beautiful inductive argument. This is how we bootstrap one thing to another. So the proposition is that if V sigma W is degree 1, commutes with L, commutes with the Lefschetz form, okay? And sigma is injective on negative degrees, then HR for W implies HL for V. And then if also sigma preserves primitives, okay, or preserves in degree minus I. So it sends to something in degree minus I to this. Then HR of W implies HR of V in that degree. Okay? Because in fact, if this was positive, then that was positive. Okay? So if you preserve the primitives, then the sign of the primitives here is the same as the sign of the primitives there, which is alternating plus or minus. Okay? But this will never tell you anything about degree 0. Because if you start at degree 0 and then apply sigma, you're at degree positive. And once you're positive, you're clearly not primitive. So you're clearly never going to send primitives in degree 0 to anything. Okay? So this is why I said 0 is the hardest thing. You can't deal with it by induction.
Sorry, I'm very confused. What do you mean HR in that?
Yeah. So what I mean is that HR of W implies that that the form restricted to the primitive subspace is plus or minus definite, depending on some sign. This is only ever going to help you in negative degree, and there are various conditions which would imply this. So if, in fact, sigma were also surjective to positive degree and maybe an isomorphism above certain degrees, then you can deduce this, that sigma must preserve primitives. So these kind of arguments are useful. Okay, that was 15 minutes, not 5. So the question is, should we stop or do you want me to tell you the geometry that inspired all this? Because I don't have very much left. And this is all background. This is just nothing that I'll actually be using. So it's just some geometric history. Or just the geometric statements. So let X be a smooth, projective, algebraic variety. With complex dimension n. Okay. Its cohomology ring is a graded ring, graded vector space. It has Poincare duality. And that implies that the dimension of Hn plus I is the dimension of Hn minus I. So it's not centered around 0, it's centered around n. But this is silly, you should just recenter it so it's around 0. Okay? And there's an intersection pairing between these two spaces. Okay? And what this intersection pairing is really multiply them together and then integrate against the top the canonical top cohomology class. So this is really exactly what we've been doing. That's why this is called this. So you have an ample line bundle. And you have its first Chern class living in H2. Now, 2 is an even number. So this first Chern class is in the center of the ring. And so multiplication by it gives you a Lefschetz operator. This is in the center of the cohomology ring. So it gives a Lefschetz form, Schetz operator. Which gives a Lefschetz form. So then we have the hard Lefschetz theorem, which is that this operator has HL. And I suppose then there's also the other theorem. It has HR. Okay, so this is the context in which this stuff. In order to state this theorem, I've been assuming our vector space is even or odd. Okay? So assume H star of x is even, right? Which after balancing is either even or means it's either even or odd, but H0 is always non-trivial, so even. Which can happen when you have some sort of filtration by complex orbits, by complex affine orbits. For instance, for flag varieties or Grassmannians. So historically, Lefschetz came up with the proof of this, and the proof was wrong. And then it wasn't proven until sort of the wave conjectures were understood. Basically, he did everything except his argument for degree 0 was wrong. And the actual correct argument that they ended up with for degree 0 really relied on something magical and special about some pi1 action that's very difficult. And then De Cataldo and Migliorini gave a new proof, which was much nicer. This is sort of the argument we like to follow. By the way, there is a statement about what HR is when it's not an even ring. You just have to, there's just complex, like the signatures now are, can be complex. It's just nastier. Okay, so the idea of proof. Okay, so if you choose a generic section in the sections of L, then its vanishing, since you chose a generic section, will itself be a smooth projective variety. Its vanishing is so-called a hyperplane section, is a hyperplane section which is smooth y and x. Let's call this inclusion map iota. Okay? So by induction on dimension, so the dimension of y is 1 less than the dimension of x, we can assume that H star y has HL and HR with respect to the same line bundle, because it's ample for x, therefore it must be ample for y. So now we can compare these two spaces. So there's two maps that we have on cohomology of projective spaces. We have push forwards and pullbacks. So I is a map from y to x. So I pull back goes here. I push forward goes there. And I pull back preserves degree, because that's what you do on cohomology. I push forward goes through Poincare duality, so it actually increases degree by 2. But then the centers of these things are different, because they have different dimensions. So actually, if you work it out, then this thing is a map of degree +1, and this is a map of degree -1, after recentering. Recenter. So this map of degree +1 is going to be our sigma. Okay? And the composition So these are bi-adjoint. With respect to the adjunction forms. And their composition is multiplication by the Chern class of L. So this is one reason you might be an isometry for the Lefschetz form. If you have an adjoint, and your composition with the adjoint is the Lefschetz form, then you can immediately see that that in fact you're an isometry for the Lefschetz form. So this explains why I star V, I star W is equal to VW. Because you just pull one of these over to the other side by adjunction, and then you get C1 of L, which is exactly what you want. Okay. So then the crucial step is the weak Lefschetz theorem. I'm going to leave the proposition up. So the weak Lefschetz theorem is what allows us to use this proposition, okay? And it's the statement that this pullback is injective from negative degrees. And in fact, it's an isometry. An isomorphism to negative degrees. Okay? So what do I mean by this? That I mean that when you start in degree -5, going to degree -4, it's an isomorphism. Degree -2 to degree -1 is an isomorphism. Degree -1 to degree 0 is just injective. So degree 0 of hy is much bigger. But degree -1 of hy is governed by degree -2 of x. Okay? So, everything is the same except degree 0 of hy can be enormous. Okay? And then similarly, I star is surjective from, it's a map of degree -1. So let's say from positive degree, and it's an iso to positive degree. And you can use these to determine that it preserves primitives everywhere except the middle. Okay? So this implies we can use the strong form of the proposition. And that's how we get hard Lefschetz on H star of x. Okay? And how we get HR everywhere but degree 0. So all that remains in the inductive proof is computing the signature of the intersection form on the middle degree. And showing that it's as you expect it to be. So you know all the other signatures. And so this is done with some sort of limiting argument. And I'm not going to go into that. Okay. But so what we're going to do is something very similar. We're going to find these two maps. Oh, sorry, these are both degree +1. Ay. Whew. They're both degree +1. Here's one, here's the other, this goes there, that goes back, and their composition is degree 2. So, which means that probably this is from 2.
That's what you just had.
Yeah, whatever. 2 from. That's correct. Yeah, the idea is that unless you're dealing with 8 of degrees, the middle degree of y, you're fine. Whew, that was close. Sorry about that.
So how are you going to do this? So you're saying an induction and this Lefschetz linear algebra part will give you everything except that.
Yes.
That's the content of what you're saying.
Well, okay, so we don't have the weak Lefschetz theorem. We're going to end up using the weak form of the proposition. So our actual inductive argument will be to just get HL this way. But it will be to get a HL for a broad class of maps. Not just the ones we're interested in, but also some other things. Okay? So actually, like the big point in De Cataldo and Migliorini proof of the Lefschetz of the decomposition theorem is actually that it's not only ample line bundles that have HR, but relatively ample line bundles have HR for some purposes. So things that aren't quite ample but are on the wall of being ample. Okay? So if you can show that they have HL, then the limiting argument says that they actually have HR. Okay? So we use this argument to say that not only ample things, which is, but actually some things on the wall have HL. And then we use some very, very large number argument to say that something has HR. And that deduces HR everywhere. So really, really, we only need HL. And so we're only going to use the weak version of this proposition.
And how do you do this part?
Yeah. So I actually don't know off the top of my head.
No, in your case.
Oh, in my case. Oh, no. But that's the thing. We sort of do a slightly different thing, right? We have the weak version of the proposition. So we don't even care about degree 0 in a special way. We actually need everything. But we actually compute all the signatures via some an argument of large numbers. And actually, we end up trying to compute that a lot of signatures are 0. So think about what happens when you take an SL2 representation, tensor with the standard representation, and look at the graded ranks and what signatures they should induce. Almost all of them should be 0. You have this signature as +1, that one was -1. They cancel out almost everywhere. So we end up showing that a lot of signatures are 0.
Okay, let's thank them.